Hello, hello, hello. Hello, hello, hello. So I'm going to discuss the general definitions of acids and bases. The first one that you come across is Arrhenius acid. This one should be just any chemical that dissolves in water to give H plus. That's going to be Arrhenius acid. It dissolves in water to give H plus. The H plus is called a proton. So for example, if you put HCl in water, it's going to break down to H plus and Cl. In other words, HCl plus H2O, that's the water, will give you H3O plus Cl minus. Okay, so the lone pair takes out the hydrogen. The two electrons that make the bond are given to the chlorine. Okay, so you can see you're making a proton. The proton is actually the extra hydrogen in H2O, which gives you H3O plus. Now, for the Arrhenius base, that's going to be a chemical that dissolves, or compound that dissolves in water to give OH minus. For example, you put sodium hydroxide solids in water, you're going to get Na plus and OH minus. The OH minus is called hydroxide. So that's evidence for the base. Okay, the next type of acid is called Bronsted Lowry. This is just an improved definition of Arrhenius. With this one, it's just simply gonna be a proton donor. If it's Bronsted Lowry acid, it's gonna be a proton donor, and in that case, Bronsted Lowry base will be proton acceptor. So example of a proton donor again is HCl. You drop HCl in H2O. The hydrogen will be taken out from the acid. Acids are proton donors, and it will be accepted by the water. So you're going to get H3O plus Cl minus. So in this case, this plays the role of an acid, this plays the role of a base. When H2O takes out the hydrogen, it gives you conjugate acid, and then the Cl minus that fell off will be conjugate base. So this was donated. So HCl is a Bronsted Lowry acid. Okay, so what about Bronsted Lowry base? I could give you a proton acceptor, which is Bronsted Lowry base. For example, if I take HCl and put it in ammonia, the lone pair on the Lewis structure of ammonia will take out the hydrogen from HCl. So this will play the role of an acid. It's donating the proton. This plays the role of the base because it's accepting the proton. It's a Bronsted Lowry base. So NH3 will change to NH4. with a plus for more charge and Cl minus. So again, this will be the conjugate acid and this will be the conjugate base. So ammonia is an example. Even this water right here is Bronsted Lowry base because it's accepting a proton. Proton acceptors are Bronsted Lowry bases. And then we have another one, which is Lewis acid and Lewis base. So let's talk about Lewis acid and Lewis base. So Lewis acid versus Lewis base. Lewis is the name of the scientist. So Lewis acids are lone pair of electron acceptor. They accept lone pairs of electrons. And Lewis base will be lone pair of electrons donor. Okay, so one donates, the other one accepts. Let's give examples here. So here's an example of a Lewis acid. So if you have, let's say you have ammonia and react it with something like boron. Boron only has 6 electrons around it in complete octet state. So to be octet, boron can take 2 more electrons. Each bond is 2 electrons, so there are 6, so it can take 2 more. If this happens, where the boron is an electron acceptor, which means it's Lewis acid. If this happens, this is the product you will get. So the ammonia will be attached to the boron structure. Okay, ammonia will get a positive charge, the nitrogen get positive charge, boron negative charge. That's the product. So if ammonia donated the electrons, it's gonna be an electron pair donor, and it's gonna be the Lewis base. Remember the BF3 will be the Lewis acid. So actually, all you're concerned with is, are we donating or are we accepting electrons? So again, the Lewis base, our ammonia right there is a Lewis base. Lewis acid, BF3 will be a Lewis acid in this reaction. Okay, because Lewis base, it's electron donor. Lewis acid is electron acceptor. Okay, so you can have another example here of Lewis base and Lewis acid. Let me see, we can use this other example. So let's say you have H2O and it's reacting with AlCl3. Again, we're using a mechanism. You expect water to use its lone pair to attack the aluminum. Nothing leaves. So these 2 electrons are given to the aluminum. So this is your Lewis acid, and the water will be your Lewis base. The arrow, double-ended arrow that I keep using, just shows movement of 2 electrons. So in other words, your H2O is now bound to the alumina metal. So oxygen will bear plus charge. If you do the formal charge calculations, Al will bear a negative formal charge. Okay, so again, Lewis base donates electrons. Lewis acid accepts electrons. Okay, so I think that should be clear. There is more reasons why this will happen that you should discuss in electron configurations chapter, because in alumina you have 6 electrons around the alumina. It's not octet. Boron is 6 electrons, so that's why they can take extra 2 electrons. All right, see you soon again for more chemistry.